So because it's a nice sunny day today, for once, we're going to be a bit flexible. We're actually going to extend the afternoon break by half an hour. So the talks will start at 5 p.m. Okay, I think it's Tommaso Gianantonio is the first talk at 5 p.m. Okay, so instead of 4, everything else will stay the same. It's just that the break will start half an hour later. So the talks will start half an hour. The break will start at the same time, so you'll get half an hour extra, okay, to spend on the beach or do whatever you want. Okay? Okay. All right, and final lecture of Will Percival's 3-lecture series starts now.
Okay, thanks. So I guess the pressure is on me to finish early as well, to give us more beach time. But that was the message I got. Right. Okay, so we're going through this equation for the linear galaxy power spectrum. If you remember, we've done projection of the clustering, we've looked at baryon oscillations, we've looked at the matter density, other talks have looked at the neutrino mass, FNL. The final component that I'm going to cover in this lecture is Ricci space distortions. That's going to cover about half of the lecture, and then the final half of the lecture will be on future surveys and some of the issues that we're going to face in the next 10 or so years. Okay, so we saw this again in one of the previous lectures, that the velocities are important in the universe. The growth of structure all follows from the peculiar velocities. And the galaxies themselves that we observe act as test particles within this flow of matter. So this, in one hand, is a very good thing. It isolates redshift space distortions, and it isolates the velocities from the properties of galaxies. So if you think of a particular location in space in the universe, then you can put a massive galaxy, a small galaxy, a blue galaxy, a red galaxy at that place in the universe, and they will all have the same velocity because they're all tracking the flow of the matter. So if we could measure the distribution of velocities that galaxies have, you might think that we would know the distribution of velocities in the universe. There is a small caveat to that, and it's one that's just being explored now, is that we require the statistical, although galaxies are locally acting as test particles, if we measure the distribution of their velocities, we require that distribution to be unbiased. So you can, if you're really, really nasty or feeling like you want to throw some spanner into the works, stop the theory working, you can imagine that if galaxies, for example, formed at special places in the universe where there was zero peculiar velocity, then there's going to be zero peculiar velocity through the whole evolution of the universe. They're not going to have any Ricci space distortions. In fact, they're going to have a particular fixed clustering pattern. But we don't think that happens in Gaussian random fields for the locations that galaxies form at, and we think that actually the distribution of galaxies the distribution of velocities of galaxies forms a very good representation of the distribution of velocities of the matter that is out there on the whole. So linear theory, and I'm not going to go through this calculation, tells us that the power spectrum of the velocities is proportional to the power spectrum of the overdensities times this factor, which includes f, which is the logarithmic growth rate derivative with respect to the scale factor, and that's why f comes in to redshift space distortions. The velocity power spectrum also has a k to the minus 2 term. This is from the operator that affects the velocities. And this means that velocities tend to pick up fluctuations on larger scales than the overdensities. Okay, so redshift space distortions. When we're making a map of the universe, we are taking the measured angles and the measured redshifts in particular and translating those through into co-moving distances, assuming we have Hubble-like expansion. So any velocity that a galaxy has in addition to the Hubble expansion rate will be picked up and will be mistranslated when we analyze the survey and translate into co-moving distances. And that means we will get the co-moving distance wrong to those galaxies. This wouldn't matter if it was an incoherent addition. If it was just noise we were adding in, we'd say, oh, actually, there's some fundamental limit on how well we can measure distances. But actually, this component that's added to the distances by doing this is coherent, and it's coherent with the structure because the velocities themselves are coherent with the structure, at least at linear order. So we measure a redshift space position for our galaxies, which is equal to the real space position, plus this term which depends on the velocity of the galaxy, the peculiar velocity, the velocity of the galaxy in a co-moving frame, along the line of sight to the galaxy. And it's tradition to denote a redshift space quantity as S and a real space quantity position as R. So there are two key regimes in terms of this peculiar velocity adding to our co-moving distance estimates. One is on linear scales, on large scales, and one is on non-linear scales. So let's go through the linear scale first. So these are representations, they're not very good ones, but they are, of clusters of galaxies. And each of these little black dots is supposed to be a galaxy. And we're supposed to be viewing these clusters as if we're viewing them from below. So in real space, actually out there in the universe, these clusters are spherical. But if we have a cluster of galaxies, or a void, sorry, this side's a void, this side's a cluster. If we have a cluster of galaxies, then on average, galaxies are falling into that cluster. Clusters are enhancing the overdensity. They're getting more and more massive. If we have a void, then on average, galaxies are moving away from that void. So here, if we observe this cluster, then we find that the galaxy on the near side of the cluster to us is moving away from us slightly more than we would expect from the Hubble expansion. And the galaxy on the far side is moving towards us slightly more than we would expect. And consequently, that cluster is squashed along the line of sight. So although there is a spherical cluster out there in the universe, we see a squashed version of it. Similarly, for a void, we see a stretched out version of it. People say that, I've seen it written in papers and it always irritates me, so please don't do this. They say that redshift space distortions arrive because galaxies fall into clusters. That is half of the story, okay? Galaxies are also moving away from voids. In fact, out there in the universe, there is this field of velocities, rather like there's a field of overdensities. And it's that field of velocities that you're picking up with redshift space distortions, not just some infall onto clusters. Okay, so this squashing of clusters, stretching out of voids along the line of sight, works to enhance the power. You get stronger clustering along the line of sight than you do across it. Excuse me. On small scales, you see a different effect. Here we have a cluster. Again, we're observing it from below. It's a spherical cluster. But now on very small scales, the galaxies within that cluster have forgotten all about infall. They are just orbiting around the center of mass of that cluster with some orbital virial motion. And in fact, that virial motion dominates the differential position of the galaxies within the cluster. So in fact, the differential redshift of two galaxies within a cluster tells you very little about their position because, as we discussed in one of the previous lecture, once you've got infall, you've forgotten about the Hubble expansion. Any delta z that you've got is just driven by the peculiar velocities. These peculiar velocities can be quite large, and when translated, mistranslated, with the Hubble expansion rate into co-moving distances, they can give strong, large, coherent distances, co-moving distances. And so clusters appear very stretched out along the line of sight. And this is referred to as the finger of God effect, because if you look at a galaxy survey, although these aren't physical structures out there, if you look at it and if you translate naively, as we all do, redshifts into distances, then you see clusters are stretched out along the line of sight to us. It's rather like fingers of God pointing at us as if we were at a special place in the universe. Okay, so most of the cosmological signal from redshift space distortion comes from the first of these two effects, the linear structure growth effect. So let's just go through the derivative of how this affects the power spectrum. This is the derivation that was first produced and published by Nick Kaiser in 1987 in this very famous paper. So the idea behind it is you've got this transition between a redshift space coordinate for a galaxy, the real space coordinate of the galaxy, and the velocity that galaxy has, the peculiar velocity, the co-moving velocity, along the line of sight. This is a transformation of two fields, a redshift space field and a real space field, and that transformation has a Jacobian. You can write it down just from this equation. This is how the volume element changes between these two fields, the redshift space and the real space field. This translation between redshift space and real space also conserves galaxy number, right? Galaxies are not appearing out of thin air, they're not disappearing, they're just moving. So we can write down conservation of galaxy number as well. And in fact, these two equations are all that we need in order to determine how redshift space distortions affect the overdensity. There is a trick in order this term, the dV by dr along the line of sight, that if you write this as basically a vector field equation and then translate into Fourier space, you see that actually it simplifies significantly and it gives mu squared theta, where theta is the divergence of the velocity field. So as an exercise, you take this equation, take this equation, take this equation, and to first order, you find this. You find that the overdensity in redshift space is equal to the overdensity in real space, and then you have an additional component which is determined by mu squared theta. Mu squared, as you remember, is the co-moving angle between in this case, Fourier mode and the line of sight, and theta is the divergence of the velocity field. Okay. Now in the power spectrum, the power spectrum, if you remember, is the two-point function of the overdensity, so the redshift space power spectrum is the two-point function of delta field in redshift space. So we have this squared here. Now, in writing this down, I've done something subtle that we'll talk about a little bit in a minute, but what I have said is that mu is the same for both of the deltas that I'm looking at. And we'll come back to that point in a minute. But if you do this and basically just expand this out, you find three components with different dependencies on the line of sight. You find what is in effect the true power spectrum of the galaxies in the universe. You have an additional component which is the cross power between the velocity and this divergence between the overdensity and this divergence of the velocity field. And then we also have a power spectrum term which is the auto power spectrum of this divergence of the velocity field. Okay, now if we include our linear theory assumptions, one of them for a linear deterministic galaxy bias, one of them for our linear velocity field, and writing out f, then this simple model becomes this. We basically have that the redshift space power spectrum is proportional to the real space matter power spectrum times this factor, which is b plus mu squared f all squared. Now, when you measure the amplitude of the power spectrum, you're measuring that amplitude of the measured redshift space power spectrum with respect to the line of sight. You're measuring the amplitude of each of these components. This amplitude depends on b squared times sigma 8 squared. It depends on the amplitude of the power spectrum in matter power spectrum, which is sigma 8 squared, multiplied by this bias factor squared. The amplitude of this depends on f times sigma 8. It depends on the matter power spectrum, but now multiplied by this f factor. This depends on b sigma 8 times f sigma 8. So you can see that the amplitude of this function, measured as a function of mu, depends on b sigma 8 and f sigma 8 through these different components. And that's why almost all redshift space distortion measurements now are written in terms of f sigma 8, because that's the component that controls basically the amplitude of the velocities, the velocity power spectrum, that is added in for these redshift space distortions. This is a linear model. It breaks down in a large number of ways, and I've just listed some of them here. One is the real to redshift space mapping. The Kaiser derivation was a first order derivation in the overdensity and in theta, this divergence of the velocity field. On smaller scales, you can go to higher order. It also assumes an irrotational velocity field. So as you go to higher order for the velocity field, you also have to allow for rotational components. The density field itself becomes nonlinear. The velocity field itself becomes nonlinear. We have fingers of God. And this approximation that we did when we went from an overdensity delta through to a power spectrum by assuming that the mu values were the same for the two overdensity components. This also breaks down, and this is called the plane parallel approximation. It breaks down for galaxies that have a wide angular separation. We also assume a local deterministic density bias in that model. So here's a plot just showing the wide angle effects in more detail. You can imagine that what we're doing this two-point function. Your mental image when I've said power spectrum, hopefully now is pairs of galaxies on sticks, but somehow translated into Fourier space. Suppose we have two galaxies that are separated by a large angular separation. So one's over here and one's over here. Then the redshift-based distortions are coming along the line of sight to each of those galaxies. We're getting each of those galaxies' distances wrong. So the galaxy in this direction, we're moving slightly this way. The galaxy over here, we're moving slightly this way. It's no good trying to fit that situation with a model in which you've assumed that the redshift-based distortions from this pair of galaxies are parallel. And that's what a lot of people do. But you can, and there's some nice, really neat derivations given out in these two papers that show an extension of the derivation of the Kaiser model, but now allowing for this differential direction of the redshift-based distortion. Basically, your power spectrum now is no longer just a power spectrum of k and mu, it's a power spectrum of k, mu, and theta, where theta is the angular separation that you're looking at. And in fact, it's simpler in the correlation function rather than the power spectrum. The good news is that all of these different effects are small. And this is shown in these plots. That they're a little bit complicated, so I'm going to take a little bit of time to explain them. What they are is the correlation function monopole and quadrupole as a function of separation. And they're not the straight monopole and quadrupole. They're the error in the monopole and the quadrupole. And then the error for different of these effects. So this is combining statistical error, which is shown by the solid line, compared to the systematic error if you had ignored any of these effects in doing the analysis. And in order of importance, the effects are nonlinear BAO damping. So this is allowing for this damping of the BAO by these growth bulk flows. The next most important effect is the nonlinear matter power spectrum. So that's the turn-up that we saw on small scales from nonlinear structure forming, where we no longer have a linear theory power spectrum. The next most important effect is the fingers of God, so allowing for the fact that clusters are stretched out along the line of sight. And then the next most important effect is this wide angle effect. And this is for a galaxy survey. This is actually done for the Sloan 2 luminous red galaxies. It's a sample very similar to BOSS in terms of the sizes of all of these effects. It's a logarithmic plot, so you can see that the signal we get, the statistical signal, is still an order of magnitude roughly larger than any of these effects, and it's a couple of orders of magnitude larger than the wide angle effects. Even so, as you go to smaller scales, these effects become more and more important. And so one of the things that people do tend to do is to include a model for the fingers of God, and they take the standard model that we saw for the linear power spectrum, and they simply multiply it by another term, and this is a damping term which allows for the fingers of God. If we assume that on small scales, galaxies lose all information about their initial positions, and we can model these velocities as a superposition of Gaussians, and this matches simulations reasonably well, then we can include a damping term in our model for the redshift-based distortions, which is given by an exponential distribution, where we have some variance which tells us basically how big, how stretched out our fingers of God are. So like many things in astrophysics, we can do this in terms of changing the model. We can also try and correct the data for this. And this is something that was done a little bit more regularly a while back. It hasn't been done so much now. And basically, you can look at these galaxy surveys, at the results, and you can try and find where the clusters are. And one way to do this is because the clusters are stretched out along the line of sight, there's no point doing just a straightforward friends of friends algorithm to find them. What you need is to find something that's asymmetric. You need a changed algorithm that basically finds overdensities, but with a kernel that's stretched out along the line of sight. And so a number of groups have done this, and what they do is they use basically a cylinder to try and find these clusters, and then once you've found one, you can try and move all of those galaxies back into a spherical configuration and then measure the power spectrum in redshift space, hoping you've removed the fingers of God so you don't have to model them. There is another way to think about redshift space distortions, and this way I think shows a lot of promise in terms of developing future models, is what's called the streaming model. And this is another way to think about the effect of moving from a real space to a redshift space field. And if you do that, then your redshift space correlation function can be written as a convolution of your real space correlation function with some term which tells you how structure is moved on average along the line of sight. So it's a pretty simple idea. What you measure, the correlation function that you measure, is a convolution of the correlation function that's out there, but just with the motion of the galaxies included between real and redshift space. And there is an increasing complexity in models for this value of P, which includes more and more options and free parameters and so on for getting this model actually right. Okay. So the final theoretical slide I have on redshift space distortions is the link between, or covers the link between redshift space distortions and the Alcott-Paczynski effect. So in the last lecture, you saw how if we get the cosmological model wrong, when we translate from redshifts to distances, we also have some sort of stretching which changes along the line of sight compared to across the line of sight. I've just told you now about redshift space distortions that are also giving us an effect that affects the line of sight. So an interesting question is how degenerate are these two effects? If you had a power law correlation function or a power law power spectrum, these two effects would be perfectly degenerate. And to think about that, you think the redshift space distortions are moving the correlation function up or down, and the Alcott-Paczynski effect is moving the correlation function across in scale. And if you have a power law power spectrum or correlation function and you don't intrinsically know what the amplitude should be, those two are perfectly degenerate and you cannot break that degeneracy and you will not measure them both simultaneously. What we have, and what this plot actually shows badly because you can't really see the dotted lines, is that this degeneracy is broken because the correlation function and the power spectrum are not power laws, and that's because of the acoustic oscillations. So this plot shows the monopole and the quadrupole, and it shows models of them, and it shows models that are designed to have the same peak position in the monopole, but have different Alcott-Paczynski effects. So you've got dA and H, the combination of them, correct to get the same peak position in the monopole, but you've got the combination of them wrong, so you have different stretching, different Alcott-Paczynski effects. You have different relative stretching along and across the line of sight. And so I hope you can see this. What it is for the quadrupole is there are three different models. There's a dotted model here, there's a solid model here, and there's a dotted model here. And so the dotted models vary this Alcott-Paczynski parameter by 10%. In the region of the quadrupole, where it's close to a power law, what this does is it changes the amplitude. And you could get this amplitude and these models to agree by changing the redshift space distortion component. Where we have baryon acoustic oscillations, we see a very different effect. The Alcott-Paczynski effect has moved the quadrupole such that it no longer looks like an amplitude shift. And as a consequence, you can break this degeneracy between the Alcott-Paczynski effect and the redshift space distortions. And this means that from the same measurements of two-point clustering, we can now measure simultaneously redshift space distortions and the Alcott-Paczynski effect. Okay, I'm going to move straight on. I'll ask for questions at the end of this section. So, this is just the results. I'll go quickly through the results because they're pretty boring. Everything agrees with the lambda CDM. Again, like baryon acoustic oscillations, I'm telling you a lot of physics, a lot of different measurements, and then I'm going to the actual measurements and then go. Anyway. This is the low redshift sample from BOSS, the monopole and quadrupole as measured from the DR12 sample. I showed these before in terms of baryon acoustic oscillations. I'm showing them again because it's the same data that's being used to measure for the redshift-based distortions. And there's a plot that Eric showed earlier this week. It shows the actual measurements themselves in combination with measurements from other surveys, and you see that they roughly agree with lambda CDM. As Eric pointed out, they're all a little bit low, which is beginning to be a minor concern. Gamma was this growth rate parameter where you are modeling the growth rate f as omega m to the power gamma. Okay, here's a slightly more interesting plot because it shows some of the, basically the dirty laundry that we have to deal with. So this is the redshift-based distortion measurements, all from BOSS, so all from the Baryon Oscillation Spectroscopic Survey. They're not all from DR12, some of them are from DR11. This side shows the low Z sample, this side shows the CMAS sample, and these are F sigma 8 measurements with error bars. This line here is the Planck lambda CDM prediction, and then the data points are all different analyses, different measurements. What's particularly interesting about this plot is that these 4 measurements all came from the same data sample. And they differed in terms of making the measurements, in terms of the modeling that they did, how they put together a model for the monopole and quadrupole moments of either the correlation function or the power spectrum. So comparing these measurements gives you an estimate of the systematic error that's coming in redshift-based distortion measurements. I should say the similar plot for baryon acoustic oscillations is very different. They are all incredibly similar between different groups, and there the systematic error is clearly subdominant. Here it's not so clear for redshift-based distortions, and that's because we are working in a regime where we need to go to the nonlinear physics. The linear Kaiser model is not quite good enough. We need extensions to that model, and depending on exactly how you put those extensions in, gives you different measurements. So you might want to throw out an outlier or two from this sample, but even so, you have systematic errors in terms of the relative offset of these different measurements that are of the same order, at least, as the statistical errors. Okay. The next half of the lecture is all about ongoing future surveys. Are there any questions about redshift-based distortions at this point? Okay.
What do you conclude? That you can work on the systematics in the future, correct them?
Okay.
That the systematic are quite correct and you actually need to change
Okay.
them.
So the question is, what do we conclude from this plot? We conclude that we need a better model. I think we need, there is work coming on the line from BOSS. The preliminary plots are out. It looks really cool. We just need to actually write it up. In terms of doing a direct side-by-side blind comparison of different modeling methods. We've done that, the results are in, and it will be published soon. I think that will show kind of similar results to this, in that the different modeling does give you different answers. I think what that means is that we need better modeling. I think one of the ways that we'll get this is through the streaming model, and by bringing together all of these different modeling ideas, putting in parameters, understanding why they differ and why they give different results. And I think there's a lot of hard work that needs to be done there, right at this interface between observation and theory. What is the model we used here? It's a model by Teruya et al. It's a Japanese collaboration. It's a reasonably simple extension to the linear theory model. It's not just linear theory. No, I went through the linear theory determination. Oh, right, okay, no. This is kind of like the next correction that people put in. In fact, even this model is not the model we fit. We need to include other terms for other nonlinear effects. That's what these models do. even so they don't agree in terms of their measurements. The solid and the open, yeah, this is low Z and C mass. The solid and the open are actually determining exactly how we marginalized over the Alcock-Paczynski effect in order to get just these redshift space distortions. 2 slides. Yes, these are just monopole and quadrupole, not hexadecapole. Yeah, and the solid line here is actually, this solid line is the average from the mocks we used to measure our errors. Yeah, it's a mocks plot. Okay, anything else on Rich's? Oh, yeah.
Yeah. Would you comment how important are the velocity bias between dark matter and baryons? If they are important to correct this or not?
Okay, so the issue here is that they are not important for this difference because all of these use the same sample, and therefore if there is a velocity bias, they have the same velocity bias inherent in the sample. So this difference we're seeing with these different data points is purely determined by the theoretical modeling. Okay. Okay, let's move on and look to the future. So Booth gave a very good talk on the dark energy survey. I'm going to just go through some ongoing surveys, some future surveys. Let's see where the field is going. Booth gave a very good talk on the dark energy survey, so I'm not going to spend any time on this. Just to say that it's not a spectroscopic redshift survey. That means it's using photometric redshifts for the galaxies. That means we have even larger error bars along the line of sight for the positions of our galaxies. And consequently, we can't measure baryon acoustic oscillations along the line of sight. We can only measure them across the line of sight. We can measure redshift space distortions, but the error bars are significantly larger than if we'd had a spectroscopic survey. And as a consequence, the large-scale structure BAO measurements that come out of DES will potentially not be as good as for other surveys. The power of DES is in the fact that it's not only doing large-scale structure baryon acoustic oscillations, but is also doing weak lensing, supernova, and cluster measurements. The follow-up from BOSS. BOSS is now completely finished. The Sloan telescope is doing another cosmological galaxy redshift survey. It's called eBOSS, and the idea is that we realized that we could actually measure redshifts for galaxies that are a higher redshift than those in the BOSS sample. And so we're using the same telescope, the same hardware, to measure redshifts for about 1 million galaxies and about, these are galaxies and quasars to do direct baryon acoustic oscillations, 60,000 quasars to do the Lyman alpha forest, out at redshifts of 0.8, 0.9, and 1.5, but with roughly the same accuracy that we've got with BOSS. So eBOSS, if you like, is pushing to higher redshifts. It's not pushing to more and more precision in terms of measuring BAO and RSD at low redshifts. And the survey has started. We have the first year of data. The big cosmology analysis will be coming out at the middle of this year. We're now in 2016, when we get the 2-year sample, which will be the first cosmologically interesting data set. And one of the cool things about eBOSS is that we are targeting quasars to use them as direct tracers of the galaxy density field. So here's a plot. This is redshift against the magnitude of quasars. And Sloan has produced the largest and the best quasar samples that we have to date. Sloan 1, 2, 3, they produced these. Are these yellow or orange? Sorry, I'm colorblind. I should look at these things up before I start talking. They produced these plots, these points. Then Sloan 3 produced these points, mainly looking at the Lyman alpha forest measurements. And now eBOSS is basically targeting redshift measurements for all of these blue quasars. So in terms of astrophysics, eBOSS will be a very interesting quasar sample to study because it pushes to 650,000 quasars with known redshifts. Okay, looking more ahead to the future, there are 3 instruments currently being built, multi-object spectrographs, designed for 4-meter telescopes. So remember right at the start of my first lecture, if you can remember, I said that This field of galaxy surveys is driven by instrumentation. There is now a rapid development in that instrumentation. We are seeing 3 new multi-object spectrographs being built. One is being built for the Mayall telescope called DESI, one is being built for the WHT, the William Herschel telescope called WEAVE, and one is being built for the VISTA telescope called Foremost. Of these, probably WEAVE is the most advanced, but it's probably the least, what's the word I'm looking for? The least, the smallest step forwards in terms of what we have at present. It has 1,000 fibers, it has a rough, to be efficient, it needs a 1-hour integration time, and consequently it won't be able to observe many galaxies at all. DESI is the one that is the most, has the most fibers, has the shortest reconfiguration time. It will be able to provide the biggest galaxy survey out of these that are coming up. The start dates are WEAVE's 2018, DESI is 2019, Foremost 2021, and of these I think DESI is the most exciting. It will cover a large galaxy survey, slightly larger than the BOSS area, and it will measure about 20 million galaxies with redshifts for BAO measurements and about 10 million low redshift galaxies. So if you think at the moment with BOSS we have roughly 1.5 million galaxies. This is an order of magnitude, in fact a factor of about 20 step forwards in terms of the sample that we'll have, the sample size. There are 2 projects building multi-object spectrographs for 10-meter class telescopes, HETDEX and PFS. They have different baseline strategies. HETDEX is targeting a relatively small area, going for high redshift galaxies, really exploiting the benefits of having a 10-meter class telescope. PFS, at least if you believe this paper, which gave a predicted survey for it, is going after more intermediate galaxies over a sort of medium-size area. And also on the horizon we have the Euclid satellite mission. Euclid is doing 2 surveys. Its primary focus is on both weak lensing measurements and galaxy clustering spectroscopic galaxy redshift survey. To get the weak lensing measurements, it's doing a very broadband optical survey over 15,000 square degrees. It's got a dichroic, basically it splits the light, incident light into visible and imaging channels, so simultaneously with the visible survey, it's doing a near-infrared survey. That near-infrared survey is swapping between photometry and spectroscopy. The photometry YJH bands and the spectroscopy is in the red band, it's GRISM spectroscopy. So rather than picking off light from individual galaxies and pushing that light down a fiber, it puts a GRISM in the optical path, so it splits all of the incident light into spectra, and then it picks up those spectra in a sort of image later on. It's targeting H-alpha emitting galaxies in the redshift range of 0.9 to 1.8, and there is a tremendous uncertainty in the H-alpha luminosity function at these redshifts, because this sort of survey just hasn't been done before, but we estimate at the moment about 25 million galaxies. Euclid will also do a deep survey, partly for calibration, partly for other science, and this will be about 40 square degrees, and it will be about 12 times the number of wide light passes, and that will help us to understand some of the confusion effects and everything that comes along from the wide survey. So in terms of cosmology summary, I could take one of these tables from any of the proposals for any of these experiments, really. This is the one from Euclid, and what it gives you is current, well, it was current when the proposal was put in, which for Euclid was about 2011. Constraints on these different parameters. We have gamma, which we talked about before. We have dark matter in terms of the neutrino mass constraints. We have FNL constraints, and then we have WA-WP dark energy model constraints, dark energy equation of state constraints. And then the standard figure of merit. This is what we had in 2011. And then this is what Euclid will give us in terms of the weak lensing plus large-scale structure measurements, combining those with clusters and so on, and then combining them with Planck give us these significantly improved figures of merit. What's perhaps more interesting, or equally interesting at least, is the legacy science potential of Euclid, and in fact all of these different projects. But what you're doing here in the name of cosmology is you're providing surveys which are of interest through a broad realm of astrophysics. So in the proposal for Euclid, a number of people, not me, were asked to come up with basically some key arguments for Euclid in terms of what it will find that we don't know now. And so this table shows that. These are a list of potential objects that we might want to know about in the universe, and then this is the number that we have before Euclid, and then this is the number that Euclid will provide. And perhaps one of the interesting ways of saying this is that the wide survey, 15,000 square degrees of Y, J, and H, just the imaging part, if you did this on a ground-based telescope, a 4-meter telescope, current state-of-the-art telescope, it would take you 680 years to do it. Okay? The deep survey would take 72 years if you dedicated a ground-based telescope to it. So in terms of the legacy potential of the surveys that we're doing in the name of cosmology, there's a hell of a lot out there. These will be a benchmark image, a benchmark set of spectra that will be used in a great many ways for many, many years to come. Okay, back to cosmology. There's a plot of redshift against the expected precision of the BAO measurement. A 1% BAO measurement would be along this line, a 10% BAO measurement would be along this line. And then the different symbols are for different surveys. This is almost certainly not right, okay? These data are almost certainly wrong. These surveys will not actually deliver what they said in the cases they will deliver. Particularly for a Euclid, we don't know what the H-alpha luminosity function is, so there is uncertainty there. But it gives you a broad picture of what's happening. Here are the BOSS measurements. We've got we've got low Z and CMAS, about 1% BAO measurements from our 1.5 million galaxies that we've observed to date. EBOS will measure another 1 million galaxies and will give us these measurements here, going out to higher redshift. DES will give us this measurement here, just from the angular BAO. Then DESI, or something like DESI, would give us a set of constraints because of the way the Fisher predictions are done for this kind of plot. These are assumed to be independent measurements, and it would give you a set of measurements that look like this, and then Euclid would be at slightly higher redshift and give you a set of measurements that look like this. So you can see that over the next sort of 5 years, while EBOS happens, we're going to push out in redshift, then DESI and Euclid come online, and there's this phase shift that we have in terms of the amount of data that we have down to these multiple measurements over wide redshift ranges. What does that mean visually? Well, here's a plot I showed a couple of years ago. This was one of the first power spectrum measurements that we had from BOSS. The effective volume was about 2 cubic gigaparsecs, and you saw the BAO in it, and we were all very pleased. This is a prediction for just one of the slices that we'll get out for Euclid. And I have made in the past similar plots for DESI, and they show the similar leap forwards. So we go from BOSS, DR9, through to Euclid. So this is the kind of transition that we saw from boomerang, maxima, CMB analysis through to WMAP. We're now facing that next leap forwards again for large-scale structure. And what this means is that we're going to have to really delve into the nitty-gritty details, right? Redshift-based distortion measurements, we can no longer afford to have systematic errors, differences between different sets of modeling that are comparable to our current statistical errors, because for this kind of experiment, they would dominate completely. So we're going to have to do lots of different things to really improve on the systematic errors and get them down to the same sort of size as the statistical errors. One of them is testing with subsamples. We did a little bit of this in BOSS. We're going to have to do a lot of it more. In BOSS, what we did was we split into blue and red galaxies, just in a simple way. They gave pretty much similar redshift distributions, and then we measured the BAO in each. And we did the same for simulations, and this plot shows the results from the simulations. It just shows that we could measure the same alpha parameters from blue or red galaxies, and we can measure the same alpha parameters depending on whether we use the power spectrum or the correlation function to do that fitting, both with very different models for the BAO.
Blue galaxies than red.
Yeah.
But in doing this plot, in doing this measurement, the number is not important, or did you renormalize?
No, we cut down the red galaxies
Okay.
to give the samples the same
Okay.
number. Okay. We're going to have to worry about getting the statistics right. We're going to have to ignore Ernest Rutherford. One of his quotes was, "If your experiment needs a statistician, you need a better experiment." Which I think was kind of fine in the era where the experiments were all lab-based and you could just do a better experiment. But in this era of these big projects that cost many billions of euros or billions of dollars, you want to get all these things right. One thing that people have started looking at more closely for large-scale structure, following on the heels of CMB analysis, is the likelihood calculation. It's pretty standard for most experiments to assume a multivariate Gaussian distribution for your data, the difference between your data and your model, with some covariance matrix that you've estimated in some way, and then use this to test different models. We know, and a lot of people have rediscovered this if you like, that if you have a covariance matrix calculated from simulations, then that covariance matrix itself has an error. In fact, the covariance matrix is drawn from what's called a Wishart distribution. That distribution has its own error. The inverse of that covariance matrix, which is what you would use in your multivariate Gaussian calculation, is drawn from an inverse Wishart distribution. And if you just invert the covariance matrix that you measure from simulations and use that as your estimate of the inverse covariance matrix, it's a biased estimator. In the same way as if you want to estimate 1 over x, you don't estimate x and then take 1 over it. Okay? Exactly the same way, if you want to estimate the inverse covariance matrix, you don't estimate the covariance matrix and take the inverse of it. You need to correct that. So that's something people have started doing. Even when you've done that, you have errors in your covariance matrix, and these errors propagate through into errors in the measured cosmological parameters that you want to go off and use to test your cosmological models. There's been a series of papers a couple of years ago that basically showed what these errors are, and really what you should do is you should form a joint likelihood of your data and your covariance matrix, both of which you have measured and both of which have an error on them. In fact, if you don't do this, you can propagate through the error from your covariance matrix into the error on your parameters and just use that propagation to correct. Even then, there are subtleties. There are subtleties depending on exactly how you derive the errors. If you derive errors from a likelihood surface that you've used to fit your data, then the errors in the covariance matrix will propagate through in a different way to if you use the distribution of mocks to estimate the errors. If you use the distribution of mocks to estimate errors and you use the same mocks that you use to estimate the inverse covariance matrix, you will get a different error on your measurement, propagating through from the covariance matrix. So I spent a lot of time, I'm ranting on about this, because I spent a lot of time worrying in BOSS that I calculated the errors we were getting on the BAO peak measurement, and I got them to be different depending on how I calculated the errors. I estimated the errors from the likelihood surfaces. Basically, you can imagine this as slightly more sophisticated version of the delta chi-squared equals 1 errors. And I compared those errors that I got from a set of mocks to the errors from the distribution of the best fits from those mocks. And they differed significantly, and they differed if I took different bin widths. And what I realized was that this was all statistically consistent with having an error in the covariance matrix. One other thing we're going to have to worry about is getting the model right. We've got very, very tight statistical errors. As we saw with the RSD measurements, getting the model right is important. It's less so for the BAO, but will become more so for this next generation of surveys. Okay, so final 5 minutes. What I want to ask is, what will the new students here in the audience be showing in 10 years' time? So my experience. I was a student in 1998. I was actually a student 96 to 99. And at the same time as my PhD, the supernova teams produced their papers showing, well, initially the Cosmology's Einstein de Sitter, then they buried that under the carpet and said it was lambda CDM, and everybody was happy. At this time, okay, this big, great paper came out that would like change the next of my 15 years of research. I paid it no attention whatsoever because I was bug hunting in some code, doing a typical PhD student. But anyway, 10 years later, all right, as a postdoc, we had concordance cosmology. We had this kind of plot that I showed before where we've got supernova, supernova, BAO, WMAC constraints, all giving us this omega m is 0.3, omega lambda is 0.7, model works well. So the 10 years since basically I was that sort of midterm PhD student to being that actually junior faculty at this point was basically the development of the concordance cosmology. So what's the world of astronomy going to look like in 10 years' time, okay? So what I did, and I did this exercise back in about 2011 when we were proposing the Euclid satellite mission, and I said, well, what will these contours look like when we have just the spectroscopic Euclid survey? And the answer is the contours will look like this, okay? So let me just, can everybody see the contours appearing here? These are the Euclid contours, right? So we have 2009 post-Euclid. Okay, and this, you know, again, I don't want to emphasize Euclid here, but the same is true from DESI. These big projects, in fact, if you combine DESI and Euclid, you could assume these go down by a √2 factor or so. So the next transition for the next 10 years, I would say, is actually more exciting for the new PhD students in the audience now than it was for me back in 1999, because we have, and we know we're going to have, this big phase shift in terms of cosmological knowledge. No longer will we just know that it's concordance cosmology, we will be delving right into the details of it. Final quote. This is an observational talk, so I have to bear this in mind. I think this is a great quote. It's a good rule not to put overmuch confidence, they used words like overmuch back in old days, in the observational results that are put forward until they are confirmed by theory. Okay? Remain skeptical, but if you end up with a beautiful, simple theory and everything matches it, that's when your skepticism can go. All right, thanks.
So we have time now for questions.
So these experiments are very expensive. And can you highlight what is DESI, in which way DESI and Euclid are complementary, or as you said, if you combine them, you get down to substantial precision. Yeah. Was that the initial aim, or is because they are born in different locations in the world and then... They
are highly complementary. First of all, there's the redshift range they cover. Okay? So Euclid has now been optimized to cover a redshift range greater than 0.9, whereas DESI covers a broader redshift range. So in terms of raw statistical power, while they are comparable, depending on whose predictions you believe, so same order of magnitude certainly, they are complementary in terms of the redshift range. I think they are highly complementary as well in terms of these results that we get out from them. We're going to have to work so hard on the systematics that having two projects with very different systematics, one space-based, one ground-based, one with a targeting catalog, one with slitless spectroscopy, one worrying about zodiacal light background, the other worrying about seeing in the targeting data. That is going to be brilliant, because if one of them finds something unusual, having another one coming along a year or so later will be brilliant.
Another question?
Measurements of the bispectrum or higher order correlations. So,
sorry, what do I expect from it?
No, not from it. Do you expect that we are going to measure them very well with future experiments?
Yes, I think we will measure them phenomenally well with future experiments. In terms of the BAO measurements, when I was talking about reconstruction, a lot of that information that reconstruction gets you back is moved from the 2-point into the higher order functions. Reconstruction moves it back into the 2 points. So in terms of the BAO distance constraints, I don't think we'll see the bispectrum bringing us a great deal. But in terms of testing galaxy formation, the astrophysics, the nonlinear processes, nonlinear gravity, I think we will see the bispectrum giving us a lot.
I hope that.
Okay.
More questions? Is there any more questions? If not, then we